Good morning, good afternoon, and good evening, depending on where you are. Thanks for attending my talk. My name is Heng Cheng. I'm an MPhil student at Hong Kong UST. Today, I'm going to talk about our work on mocking, which is an important technique in unit tests. Basically, we disclose some characteristics of when developers choose to mock a dependency, and we tried to recommend mocking decisions based on our findings. In real-world projects, it is quite natural for a class to depend on other classes or libraries to function. For example, the class account service depends on a class connecting to the database. To test the service class, we need to first prepare a database, initiate the dependency, and then start testing. However, since this is unit test instead of integration test, setting up a database is too heavy. Instead, developers may want to focus more on the left-hand side and simplify the setup process. Usually, developers may use a mock repository to replace the real one in the unit test. In this case, the mocked repository will return false directly without connecting to the database. Using such a mocked object can make the test run faster. Although mocking is powerful, it will cause issues if we don't use it properly. On the one hand, if developers didn't mock some dependencies that should be mocked, which is called under-mocking. For example, in Project Camel, they didn't mock a class that interacts with the cluster. This made the test very slow. Apart from this, under-mocking will make the test flaky or cause some side effect to the runtime environment. So, can they mock all the dependencies? The answer is no. If they mock too many classes, they may need to pay more effort on maintaining those mocked objects. Otherwise, the inconsistency between the mock object and the real one will cause false alarms. For example, in Project Flink, the mocked object returns a null value. However, the real implementation will never return null. In this case, the test failure does not show a real bug in the software. Actually, a mocking decision is not that easy to make. Developers may change their decisions during software development. According to a recent study, 13% of the mock objects are introduced after the test script was written, and 17% of the mock objects are removed afterwards. Furthermore, studies also highlighted that we need an automated mechanism to identify the dependencies that should be mocked. Therefore, in this work, we aim to answer which dependencies should be mocked. To answer this question, we designed an automated mock recommendation tool. Given the class under test and the dependency, it tells whether the dependency should be mocked. To recommend such decisions, it should analyze the code based on factors that can affect mocking decisions. To find such factors, we first check the existing work. Here are some representatives of existing findings. Although they reflect the mocking practice adopted by developers, they are high-level and qualitative, which cannot be used by automatic code analysis techniques. As such, we conducted an empirical study to find the code-level characteristics of the mocked dependencies. With such characteristics, we can extract them automatically from the code and recommend mocking decisions accordingly. Specifically, we chose 4 popular open-source projects and extracted the mocking decisions by developers from them. With the dataset, we sample a small subset for manual analysis. Based on the observation in the manual analysis, we formulated 10 code-level rules. We further validated whether these rules can effectively select the data entries that are labeled as mocked in the whole dataset. Finally, we found the characteristics in two categories are very effective in selecting mocked data entries. The first one is about API usage. Basically, we found that classes interacting with network, hard disk, and database by invoking their APIs are often mocked. Besides, classes representing an external resource may implement interfaces like Closable. Such classes are often mocked. Also, classes calling synchronized methods often performs concurrent operations, which may introduce non-determinism and thus often mocked. Another category is about the interactions between the class under test and the dependency. We found that developers often mock the classes that can affect the runtime control flows of the class under test. For example, let's look at the code snippet from Project Camel. Here, the method return value of endpoint config is used as a branch condition. Developers mocked the endpoint config. By stopping different return values, they can cover the two branches of the if statement. Besides, we also found developers stop an exception to test exception handlers. Similar to the examples we just mentioned, in the empirical study, we disclosed 10 code-level rules. However, none of them is a determinant factor. Therefore, we decided to combine them using machine learning. To connect the rules to machine learning, we turn these rules into 16 features. The features fall into 4 categories. The first is about contextual information. That is about the interactions between the class under test and the dependency. For example, does the dependency throw an exception caught by the class under test? The second are meta properties. For example, is the dependency a JDK class? The third one is API usage. For example, how many call size to a database API? The last category is complexity. For example, how many fields are in the dependency? Based on these features, we tried these algorithms and we found that gradient boosting was the best. Therefore, we used it as the default classifier in our evaluation. For evaluation, we selected 10 large-scale popular open-source projects. They are used for data processing, message routing, web service, and so on. Then, I would like to talk about 4 research questions. First, we want to see whether MockSniffer can do better than existing strategies as well as the contribution of machine learning. Also, we are interested about the performance of MockSniffer in its potential application scenarios. Since there is no existing mock recommendation technique, we chose the heuristics reported by existing studies that can be directly applied to the code as the first baseline. Basically, it mocks all the classes in the code base and all the interfaces, except those provided by the JDK. The second baseline comes from ArrowSuite, an automated text generation tool. It contains a list of candidates to mock on text generation, and we mock all the classes in this list. The third one is based on the rules in our empirical study. This is an aggressive approach which decides to mock if any of the rules match. By comparing with this baseline, we can see whether machine learning have made better mocking decisions. From the evaluation result, we can see MockSniffer outperformed the first two baselines by all metrics. Interestingly, we found baseline 3, the one based on rules in our empirical study, had higher recall than MockSniffer. This is because baseline 3 is very aggressive. It decides to mock if any of the rules match. Since none of the rules is a determinant factor, it suffered from a low precision. In comparison, by using machine learning to consider these factors holistically, MockSniffer raised the precision to over 80% by only losing less than 10% of recall. From this we can see, machine learning is helpful in recommending mocking decisions. In addition to comparing with baselines, we also evaluated MockSniffer in two potential application scenarios. First, for mature projects, there are lots of historical versions. As such, we can extract data from the historical versions for training and recommend mocking decisions on the development version. To simulate this scenario, we performed cross-version prediction on each project. As illustrated on the right-hand side, we use the first version for training, and then predict the newly appeared data entries, the orange part, in the second version. And then we use the first two for training, predict on the third one, so on and so forth. This is an incremental process. Next, for new projects, there's no sufficient historical releases for training. As such, we may collect data from open source projects to train MockSniffer. To simulate this scenario, we performed cross-project prediction. Specifically, we trained MockSniffer with 9 projects and predict on the remaining one. This procedure was repeated on the 10 projects. Finally, by comparing the results, we found that cross-version prediction can catch the similarities between the mocking practice within the same projects, and thus had higher precision. As for cross-project prediction, since it learns from multiple projects, it can cover a more diverse set of mocking practice, and therefore had higher recall. This is helpful for projects where large changes take place. For example, in our experiment, when doing cross-version prediction, we trained with OSI 4.x and predict on 5.x. Since large changes take place in the version transition, the recall is only 30% because the newly adopted mocking practices cannot be learned from previous versions. However, such new mocking practices may exist in other projects, and the recall in cross-project prediction is much higher. To summarize, we built the first mock recommendation technique and conducted evaluation in 2 potential application scenarios. In our study, we disclosed 10 code-level characteristics and released a dataset containing over 500,000 data entries. Thanks for listening to my talk. If you are curious about the details, please check out our paper or drop me an email. Finally, stay healthy, stay safe.